the angular momentum theorem. A control volume analysis can be applied to the angular momentum relation by letting our dummy variable b be the angular momentum vector h. So consider the Reynolds average transport theorem, which is in the vector form. D, let me write it blue, d beta on dp on dt equals to beta rho dv plus integral on control system or beta br dot n dA. So in the case of angular momentum, we have B equals to H. So and H equals to integration on system R multiplied to V dN. We can write beta relation as d h on dm. From these two relations, we can calculate beta equals to r cross 2v, which is a vector 4. By replacing to the Reynolds theorem equation, we now can write dh on dt, in this case dho, equals to on control S, beta is R dA. We know from dynamics, if you look at dynamics, we have this relation for the time derivation of the angular momentum equals to the summation of momentum on point O, which can be also R multiplied to F around a point O. Note that the total momentum equals to the summation moments of the applied forces about point O. Recall, however, that this law, like Newton's law, assumes that the particle velocity v is relative to an inertial coordinate system. So particle velocity is relative to an inertial coordinate system. And we can write this relation also for if not the moment about the point O of the relative acceleration term, and for the acceleration relative accelerating coordinate, we can write this relation for the momentum on point O, the summation of all forces momentum on point O and the relation of coordinate system Tm. These relations are also in the dynamics for a acceleration coordinate. Anyway, with this description, the angular momentum equation according to the Reynolds transport theorem can be obtained as dHO on dt, which is MO, which is minus so the Reynolds transport theorem can be obtained as equals to time derivation on control volume plus Theorem on control system dA. This is the relation of the angular momentum in a system. For a non-deformable inertial control volume, this relation reduces to the, so it is for a, let me write original, for any coordinate system. Relative or non-relative motion may be influenced in this relation, but for a non-deformable inertial control volume, for non-deformable inertial control volume, is the second part in the left hand side eliminated, but will be eliminated, and we can write the relation sigma MO equals to sigma equals to D on dt beta, which is R cross V rho dV plus this is the relation for the non-deformable inertial control value. So, in considering this relation, let me write again here. Rho dV plus rho VR and dA. Another simplification is when we have one-dimensional shown are inlet and outlet. Flow the part integral on control system, which cut the system of the control value of any fluid that cut the system is equals to, as previous relation for Reynolds transport theorem, out m dot out minus out m dot out. So we can write the Reynolds transport in m dot in. Let me make a correction here. This is the end of angular momentum section. There are various example solution in the solution videos first. The next description in this chapter is about the energy equation.